Hello, everyone. In this video, we will cover some examples related to the complete expectation of life involving fractional ages. Before we move on to the examples, we will provide some characteristics about the complete expectation of life under the UDD fractional age assumption. For a life age x, where x is an integer, the future lifetime random variable Tx equals Kx plus Rx, where Kx is the current future lifetime random variable, and Rx is a random variable corresponds to the fraction of the year lived during the year of death. That is, Rx should be between 0 and 1 year. Under the UDD assumption, Rx follows a uniform distribution between 0 and 1, and the random variables Kx and Rx are independent. First, let's show that Rx follows a uniform distribution between 0 and 1. Start with the CDF of Rx. The probability that Rx less than or equals S equals to the probability that Kx equals K and Rx less than or equals S, where K range from 0 to infinity. It doesn't matter what the value of Kx is. We just want the probability that Rx is less than or equals S. This probability is equivalent to the probability that Tx is between K and K plus S. In terms of the actuarial notation, this is Kpx times Sqx plus K. Under the UDD assumption, Sqx plus K is S times Qx plus K. Factor the S out, Kpx times Qx plus K is K bar Qx. This is the probability that Kx equals K. We need to sum up all these probabilities for K equals 0 to infinity. This summation is 1. And we get the CDF of Rx is S. And then the density function is 1. We conclude that Rx follows a uniform distribution between 0 and 1. To show that Kx and Rx are independent, we start with this intersection event, the probability that Kx equals K and Rx less than or equals S. The same flow, the probability that Tx is between K and K plus S, and this equals Kpx times Sqx plus K. Under the UDD assumption, we get this expression, and we get S times K bar Qx. S corresponds to the probability that Rx is less than or equals S, and K bar Qx is the probability that Kx equals K. We get a product of two separable functions of Rx and Kx, and therefore Kx and Rx are independent. Get back to the complete expectation of life, the expected value of Tx. All right, so we have Rx uniform distribution, 0 and 1, and Kx and Rx are independent. The expected value of Tx, which is the expected value of Kx plus the expected value of Rx. The expected value of Rx is the mean of the uniform distribution between 0 and 1, which is 1/2. And then the variance of Tx, due to independence, we have the variance of Kx plus the variance of Rx. The variance of Rx is 1/12. And then we get the relationship. All right, then we move on to the examples. Given that Q80 is 0.15, calculate the 0.4-year temporary expectation of life for an individual at age 80. In part A, the UDD assumption. We want to get the expected value of the minimum of T80 and 0.4. Instead of using the formal definition to do the calculation, that means the integration, we make use of the diagram. If the individual can survive beyond age 80.4, corresponds to the event T80 is greater than or equal 0.4, the corresponding expectation here is 0.4. This is the maximum. And then the corresponding probability is 0.4 P80. If the individual cannot survive up to age 80.4, then T80 is less than 0.4. In this interval, T80 follows a uniform distribution between 0 and 0.4. The expected value of this is 0.2. The probability of this event is 0.4 Q80. And now we have the probability mass function of this random variable. And then we can get the expectation of that. With the same argument similar to the De Morgan's law, we have this expression. Here we have the expectation of this random variable given that T80 is greater than or equal to 0.4 times the corresponding probability, plus the expectation of this given that T80 is less than 0.4 times the corresponding probability. And we have 0.4 times 0.4 P80 plus 0.2 times 0.4 Q80. Under UDD, 0.4 P80 is 1 minus 0.4 Q80, 1 minus SQX. And then 0.4 Q80 is 0.4 times Q80. SQX is S times QX. And we get 0.388. Let's rework part A with the definition, and then we will do part B afterwards. This is the integral of Tp80 dt, where t from 0 to 0.4. The corresponding duration is from age 80 to age 80.4 within two integral ages, 80 and 81. Under the UDD assumption, SPX equals 1 minus S times QX if S is between 0 and 1 and X is an integer. Here we have TP80, which is 1 minus T times Q80. Q80 is 0.15. Upon integration, we get 0.388. Part B, assume constant force of mortality over each year of age. SPX is Px raised to the power S, where S is between 0 and 1, X is an integer. TP80 is P80 raised to the power T. Do the integration, and we get 0.3873. The next example, we have Q70 is 0.12, and we would like to calculate the 0.6 year temporary expectation of life for an individual age 70.3. Here we have non-integral age 70.3. By definition, this is the integral Tp 70.3 dt, where t from 0 to 0.6. The interval of age involved from 70.3 to 70.9 between two integral ages, age 70 and age 71. Under UDD, we can make use of this expression, SPX plus T, where X is an integer and S plus T is between 0 and 1. All right, so TP 70.3 equals this expression, and Q70 is 0.12. Do this integration, and then we get the answer 0.5776. Part B, assume constant force of mortality over each year of age. SPX plus T equals Px raised to the power S, where X is an integer, S plus T is between 0 and 1. So we have TP 70.3 is P70 raised to the power T. And we get P70 equals 1 minus 0.12, which is 0.88. Upon integration, we get 0.5776. The next example, given that Q60 is 0.1, Q61 is 0.16, calculate the 1.4-year temporary expectation of life for an individual aged 60.2. By definition, we have two terms. The first term, we move the individual at age 60.2 to an integral age that is to age 61. So we do the integration first, the first expectation. TP 60.2, assume that the individual can survive only up to age 61. And then plus the probability that the individual can survive up to age 61, and then the expected future lifetime afterwards. All right. We have SPX plus T written in terms of the conditional probability. A person currently at age X plus T, the probability that this individual can survive beyond age X plus T plus S equals to an individual at age X can survive beyond age X plus S plus T, given that this individual at age X already survived up to age X plus T. Under the UDD assumption, part A here, the first term, we have this expression using this relationship. And then the second term, 0.8 P60.2, which is P60 over 0.2 P60. And then TP61 is 1 minus T times Q61. Here, this involves the duration of age from age 61 to age 61.6. And then we get this expression. T plus 0.2 P60, this is 1 minus T plus 0.2, 0.1. T plus 0.2, T is from 0 to 0.8. So T plus 0.2 is from 0.2 to 1. And then 0.2 P60 is 1 minus 0.2 times 0.1. 0.1 is Q60. And then P60 is 1 minus 0.1, so we get 0.9 in this second term. 0.2 P60, 1 minus 0.2 times 0.1. And then 1 minus TQ61. Q61 is 0.16. So we have the integrand 1 minus 0.16T in the last term. Do the integration. And then we get the answer, 1.2919. Part B, constant force of mortality. We have SPX equals PX raised to the power S, and SPX plus T equals PX raised to the power S. The first expression, X is an integer, S is between 0 and 1. The second expression, X is an integer, S plus T is between 0 and 1. All right, so we have TP60.2 is P60 raised to the power T. And then 0.8 P60.2 is P60 raised to the power 0.8. And TP61 is P61 raised to the power T. We have Q60 and Q61, so we can get P60 and P61. Upon calculation, we get the answer 1.2908. That's it for today's video. Thank you for watching and see you in the next video.